Good morning, one and all. Myself, Dr. B. Surendranath Reddy, Assistant Professor in School of Mathematical Sciences, Swami Ramanand Tirth Marathwada University, Nanded. Today, I will discuss on continuous functions and their properties, especially uniform continuity of a function. I'll first give sequential definition of continuity. So let's start A subset of R, and F is a map from A to R. Then sequential definition of continuity is the following. A function f is continuous at a point A if for every sequence xn in A with xn converging to A, we have f of xn converging to f of A. So if this condition is satisfied, we say that f is continuous at A, and suppose if f is continuous at every point, at every A in A, then we say that f is continuous on set A. Okay, so this is the definition of continuity in terms of sequences. So let's consider some examples. Take simple one. Take first constant function f of x is equal to c, where c is any constant, real constant. Then f is continuous, because if we take a sequence xn converging to A, then this f of xn is c which converges to C, and this is f of E. So therefore f is continuous on R. So every constant function is continuous. And next one is identity function f of x is equal to x, which is also continuous, because if xn converges to A, then f of xn is xn when it converges to A, which is f of A. So therefore identity function is also continuous. In the same way, you can prove that f of x, which is equal to x power n for n greater than or equal to 1, is also continuous on entire real line R. Now, when we say that function is not continuous at a point, so f is not continuous at some point A if there exists a sequence xn in A such that xn converges to A, but f of xn does not converge to f of A. So if we can produce a sequence which converges to this given point A, but f of xn does not converge to f of A, then we say that f is not continuous at this point. So let's have some example. of non-continuous function, take Dirichlet function, famous function, f of x is 1 if x is a rational number, 0 otherwise. This is called Dirichlet function. We'll show that this function is nowhere continuous. So to prove that, f is nowhere continuous. So take any point, first take any, we will prove that f is not continuous at all rational points as well as f is not continuous at all irrational points. So let a is a rational number. Then by density of irrationals, then there exists a sequence xn in irrationals such that xn converges to this a. Now suppose f is continuous, then f of xn, but we know f of xn because xn's are irrational, f of xn is 0, okay, and f of a, which is a is rational, so this is 1, so we get that therefore f of xn does not converge to f of a, and hence f is not continuous at any rational number. Similarly, if we take a, which is an irrational number, then by density of q, there exists a sequence in q such that xn converges to a. So in this case, f of xn is 1 and f of a is 0. So hence, in this case also, f of xn does not converge to f of a. So therefore, f is not continuous at any irrational number. So therefore, f is nowhere continuous. Nowhere continuous on R. Now let's have another example, f of x, which is 0 if x is less than 0 and 1 if x is greater than or equal to 0. So how graph of this function look like? We will draw the graph of this function. Then we know that if x is less than 0, then f of x is 0. So this is f of x, and if x is greater than or equal to 0, that value is 1. So this is graph of this function. Now we can see that from graph, f is not continuous at 0 and it is continuous everywhere. So we will prove that. Suppose let a is less than 0, then we have to prove that this function is continuous. So for this, suppose there is a sequence xn converges to a. Then in particular, for epsilon, which is minus a by 2, there exists a natural number k such that mod xn minus a is less than epsilon for all n greater than or equal to k. So that is a plus a by 2, which is less than xn, which is less than a minus a by 2. Okay, so this shows that xn is less than a by 2. This is true for all n greater than or equal to k, but since a is, this implies we conclude that xn is less than 0 for all n greater than or equal to k. So therefore f of xn is equal to 0 for all n greater than or equal to k, and hence f of xn converges to 0, which is f of a. So it shows that this function, therefore f is continuous at a if it is less than 0. Similarly, we can prove that f is continuous for every a greater than 0. By similar argument, we can prove that f is continuous for every a greater than 0. Now, let a is equal to 0, then by diagram suggests that it is not continuous at 0. So if we want to prove that f is not continuous at 0, it is enough if we give a sequence xn which converges to a, but f of xn does not converge to f of a. So for this, take sequence xn which is minus 1 upon n, then we know that this xn converges to 0, but what are f of xn's? Because they are all less than 0, so you will get 0, and f of 0 which is equal to, so then f of xn converges to a which is 0. So f of a, because a is 0, this value is 1. So therefore f of xn does not converge to f of a, and hence for f is not continuous at 0. So in this way we can show that f is not continuous, therefore this function f is not continuous at x or a is equal to 0, and everywhere else it is continuous. Now we'll give another definition of continuity, that is epsilon delta definition. So we say that f from a to r is said to be continuous at a point a in a if for a given epsilon greater than 0 there exists a positive real number such that x is in a and mod x minus a is less than delta, then mod f of x minus f of a is less than epsilon. If given any epsilon, if we can find such a delta such that whenever x is satisfying x minus a is less than delta, then f of x minus f of a is less than epsilon. So what it mean pictorially is, we'll see, try to understand through the graph of the function. So this is the how any continuous function, definition of continuous function. So given any point a, here we have f of a, and given any epsilon, we want whenever some x is in this neighborhood, then f of x should be in this neighborhood. If it is satisfied, then we say that f is continuous at a. So let's see some example how to prove. So take f of x square on R. Then we will prove that f is continuous at every point in R. So let a is any point. Then we have to estimate f of x minus f of a, which is x square minus a square, and this is mod x minus a into mod x plus a. Now suppose assume that there is a delta, there exists a delta such that mod x minus a is less than delta. Now if this delta works, then for any delta prime which is less than delta also works. So in particular, delta prime by delta also works, which is less than 1. So assume that mod x minus a is less than 1. Okay, then mod x same as mod x minus a plus a, which is less than or equal to mod x minus a plus mod a, so which is 1 plus mod a, and mod x plus a, which is less than or equal to 1 plus 2 times mod a. So now if you go back to this one, f of x minus f of a, so f of x minus f of a, this one is, it is equal to mod x minus a into mod x plus a, but which is less than mod x minus a into 1 plus 2 times mod a. Now we want to find a delta which is less than, so this is less than delta times 1 plus 2 mod a. Now we want this is less than epsilon, so that is in particular we want delta which is less than epsilon by 1 plus 2 mod a. And here if you see this, we also want delta is less than 1. So therefore take delta minimum of 1 comma epsilon by 1 plus 2 mod a. Then whenever mod x minus a is less than delta, we have proved that mod f of x minus f of a is less than epsilon. So it shows that f is continuous, therefore f is continuous at every point, so f is continuous on R. Now if you see this one, our delta is depending on a as well as epsilon. So if we change a, this delta may also change. Okay. Now let me ask a question. Suppose f is continuous, f is continuous and xn is Cauchy in A. Now is f of xn is a sequence in R is Cauchy. So answer is no, because take a function f maps from 0 to infinity to R by f of x, which is 1 upon x. Then we know that 1 upon n is a sequence, is Cauchy sequence, but f of this xn's, which is n, is not bounded, so hence it is not Cauchy. Okay, so every continuous function need not take Cauchy from Cauchy sequence to Cauchy sequence. Now, another question I can ask is, if you see this example, our delta depending on A also. So question is, given any epsilon, can we find a delta greater than 0 which depends only on epsilon and works for all A in A? And if such delta exists, then that function is called, if such delta exists, then f is called uniformly continuous. Uniformly continuous. So definition of uniform continuous is f maps from A to R is said to be uniformly continuous, if for a given epsilon greater than 0 there exists a delta greater than 0 such that for all x comma y in A with mod x minus y is less than delta implies mod f of x minus f of y is less than epsilon. So if this condition is satisfied, then that function is called uniformly continuous. So if you see this definition, uniform continuous is an entire domain. Uniform continuous is not talked on a particular point. So given any 2 points with x minus y is less than delta, we want mod f of x minus f of y is less than epsilon. So in particular, every uniformly continuous function is continuous, because that if one delta works for all A, so it is continuous. Okay. Now converse is not true. That means every continuous function need not be uniformly continuous. So what is meant by not uniformly continuous? F is said to be not uniformly continuous if there exists an epsilon such that for all delta greater than 0, okay, there exist two elements x delta and y delta with mod x delta minus y delta is less than delta, but mod f of x delta minus f of y delta is greater than or equal to epsilon. So take this example, f of x is equal to 1 upon x on the interval 0 to infinity, then this function is continuous. We'll prove that this function is continuous but not uniformly continuous on this one. So we'll show that this f is continuous but not uniformly continuous. So to show continuous, let any a point here that is a greater than 0, then we have to show that for given epsilon greater than 0, there exists a delta such that f of x minus f is less than. So we have to estimate f of x minus f of a, which is 1 upon x minus 1 upon a. So this is same as mod x minus a by x into a. But we can so this is less than mod x minus a by 2 times a square if x is greater than a by 2. So this suggests that we can take, we want this is less than epsilon, so we have to choose delta. So take delta as minimum of this a by 2, and this is less than epsilon, so we want epsilon times a square by 2. Then f is continuous, but we show that f is not uniformly continuous. So suppose if we assume that f is uniformly continuous, suppose f is uniformly continuous. Now let's see the picture of this graph, this function. So this is the graph of f of x is equal to 1 by x. Now if you see that whenever x and y are very close and close to 0, then their values are large enough. This is x and this is y, then this is f of x, this is f of y. So this suggests us that take x and y which are very close to 0 and close to each other. So given take epsilon is equal to 1, then suppose if f is uniformly continuous, then there exists delta greater than 0. So how can we choose x and y which are very close to 0? By taking x is equal to 1 upon n, where n is large. So by Archimedean property, there exists a natural number n such that 1 upon n is less than delta. Now take x is equal to 1 upon n and y is equal to 1 upon 2n, then mod x minus y will get is 1 upon n, which is less than delta. But what about f of x n? What about f of x and f of y? So f of x minus f of y, you know that this you will get n which is greater than or equal to 1, which is a contradiction that we want it is strictly less than 1. Contradiction to the fact that f of x minus f of y, we want this is less than 1. So therefore f is not uniformly continuous. Whereas if you fix f of x which is equal to 1 upon x and any positive integer, then one can prove that f is uniformly continuous. Because this is clear, because f of x minus f of y is think about mod x minus y by x into y, but x and y are greater than a, so this x minus y by is a square. Okay, so we can, so if we take delta, which is take delta less than a square times epsilon, then mod f of x minus f of y is less than delta by a square, which is less than epsilon. So this function is uniformly continuous if you fix a which is greater than 0. Another example we can give is, second example, take f of x is equal to x square on entire R, then we know that f is continuous. We will show that f is not uniformly continuous. So to do this one, let's see the picture of this and analyze where is the problem, at what points. So if you see, this is the graph of f square, f of x is equal to x square, and if x and y are large, then we have f of x and f of y is large. So this suggests to take our, so take epsilon is equal to, suppose if it is uniformly continuous, for this epsilon there exists delta greater than 0 satisfying that condition. Now by Archimedean property, there exists an n natural number such that 1 upon n is less than delta. Now take x is large, so take x is equal to n and y is n plus 1 upon n, then we know that mod x minus y is equal to 1 upon n, so which is less than delta, but we calculate f of x minus f of y, we get that f of x is equal to x square, so x, that is n square minus n plus 1 upon n whole square, and by simplification we can see that this is greater than or equal to 0, which contradicts to our assumption that mod f of x minus f of y is less than 1. So therefore this function is also not uniformly continuous. So one can ask, which functions are always uniformly continuous? So we'll define what is meant by ellipsis function. Okay. So a function f maps from a to r is said to be ellipsis, if there exists a positive real number such that mod f of x minus f of y, we want this is less than equal to k times mod x minus y for all x and y in this space. If such condition is there, if such k exists, then this function is called ellipsis function. Now we can prove that if f maps from A to R is ellipsis, then f is uniformly continuous. So we have all ellipsis functions which are uniformly continuous. The proof is simple. Suppose assume that if f is ellipsis, then there exists k such that mod f of x minus f of y is less than or equal to k times mod x minus y. Now let x and y in A such that mod x minus y is less than delta. Then mod f of x minus f of y is less than k times delta, but we want this is less than epsilon, so which suggests to take our delta as less than epsilon by k. Take delta as less than by epsilon k, then we get that this is less than epsilon. So therefore ellipsis implies uniformly continuous. The converse is not true. Not every uniformly continuous function is ellipsis. So I leave it to you to check f of x, which is equal to root x from 0 to 1 is uniformly continuous but not ellipsis. So here hint is that suppose there exists a k, such that f of x minus f of y, so in particular this is less than or equal to k times x, okay, k times mod x. So this is hint. So does there exist a k satisfying this condition? Okay. So we have proved that all ellipsis functions are continuous, and one more important useful result is that suppose f maps from a interval I to R is an interval f, suppose f is differentiable with finite derivative such that f dash of x is less than or equal to k for some k greater than 0, then we can prove that f is ellipsis and hence uniformly continuous. The proof is simple. Mainly we apply mean value theorem So let x and y belongs to I. Then because I is an interval, so x comma y is contained in I, and this f is continuous on x comma y and differentiable at endpoints in the open interval x comma y. So therefore, by mean value theorem, there exists c in x comma y such that f of x minus f of y is equal to f dash of c into x minus y. So this implies mod f of x minus f of y is equal to mod f dash of c into mod x minus y, but we know this is less than or equal to k times mod x minus y, because our f is with bounded derivative. Okay, so this shows that f is ellipsis. So the immediate consequence from this result is that f of x is equal to sin x and f of x is equal to cos x. They are all uniformly continuous. Not only uniform continuous, they are ellipses, because they are all differentiable and mod f dash of x is less than or equal to 1. Okay. These are all immediate examples. So what are all other functions which are uniformly continuous? So we can say that if we have a continuous function and a closed and bounded interval, then it is uniformly continuous. So if f maps from any closed and bounded interval a comma b to r is continuous, then f is uniformly continuous. So if we have a continuous function and a closed and bounded interval, then it is uniformly continuous. So proof of this result, suppose assume that f is not uniformly continuous. Suppose f is not uniformly continuous. What is the meaning of this one? There exists, therefore there exists an epsilon greater than 0 such that for all delta greater than 0, okay, there exists x delta and y delta such that mod x delta minus y delta is less than delta, but mod f of x delta minus f of y delta is greater than or equal to epsilon. Okay, so in particular, take, so for every delta which is 1 by n, there exists xn and yn such that mod xn minus yn is less than delta, but mod f of xn minus f of yn is greater than or equal to epsilon for all n. Okay, now since xn is bounded, because our domain is bounded, so by Bolzano-Weierstrass theorem, I make it BWT, Bolzano-Weierstrass theorem, there exists a subsequence x and k of xn such that it converges. So x and k converges to some x where x is in this a comma b. Now we can prove that this there there exists a subsequence yn k in yn which also converges yn k converges to same limit x. This is because yn k minus x, we can write this as yn k minus xnk plus xnk minus x, and yn minus xnk, we can make it this is less than epsilon, and this is also make it less than epsilon, so therefore yn converges to x. So therefore, since f is continuous and we have x and k converges to x and y and k converges to x, this implies we get that f of x and k converges to f of x and f of y and k also converges to f of x. Then using this we can find there exists a large k such that mod f of x and k minus f of y and k, we can make this is less than or equal to mod f of x and k minus f of x plus f of y and k minus f of x. Okay, so we can make this is less than epsilon for all n greater than or equal to, sorry, for all there exists k naught for all k greater than or equal to k naught. So which is a contradiction, because we have assumed that f is not uniformly continuous. That means this is true. So this is contradiction to that fact. This is true for every n, but here we are getting that if your n case greater than or equal to k naught, then we are getting this is less than epsilon. So therefore our assumption is wrong. Therefore this f is uniformly continuous. Now if you go back to our question asked during continuity, that if f is continuous and xn is a Cauchy sequence, f of xn Cauchy. So this result is true if f is uniformly continuous. So the result is that if f is uniformly continuous and xn is Cauchy, then f of xn is Cauchy, is also Cauchy. So proof that f is uniformly continuous is given to you and xn is Cauchy, we have to prove that f of xn is Cauchy. So take epsilon greater than 0, then since f is uniformly continuous, there exists delta greater than 0 such that whenever for all x comma y in A with mod x minus y is less than delta, then we have mod f of x minus f of y is less than epsilon. Okay. Now also given that this xn is Cauchy, so for this delta greater than 0, there exists a natural number k such that mod xn minus xm is less than delta for all n comma m greater than or equal to k. Now, by applying uniform continuous, we get that mod f of xn minus f of xm is less than epsilon for all n comma m greater than or equal to k, which shows that this sequence f of xn is quotient. So if a function is uniformly continuous, then it maps Cauchy sequence to Cauchy sequence.